This section explains what makes cybernetics a new kind of science. Cybernetics inverts the question a science asks of its object. Instead of asking what a thing is, it asks what the thing does. Strip away the substrate and keep the behavior. A simple harmonic oscillation is the same object, whether it lives in a wheel or in a voltage. The materiality drops out as an irrelevant coordinate. Ashby anchors this with geometry. In Chapter 1, he notes that geometry once treated only the forms drawable in terrestrial space, and now those terrestrial forms sit inside geometry as special cases. Cybernetics stands to real machines in exactly the same way. Its subject is all possible machines, and the ones nature happened to build are the incidental few. This is the whole book's founding move. Quotient away the physics, study the space of behaviors, and the actual becomes a restriction of the possible. This section explains what cybernetics takes as its subject. Cybernetics studies ways of behaving. Its question is always, what does a system do? And never, what is it made of? Ashby's compression is the geometry anchor. As geometry outgrew terrestrial objects until it contained them as special cases, cybernetics takes as its subject the whole domain of all possible machines. The ones that nature or man happen to have built are merely the actual points inside that space. Substrate drops out as irrelevant. Electronic, neural, economic, none of it matters. What survives is the pattern of determination and control. The generative move is this: replace the object with the possibility set that contains it. Then ask why the actual case obeys its particular restriction. And here is the boundary. Energy is taken for granted so that only information and control remain. This section builds the foundational vocabulary of the whole book, the idea of change stripped down to its atom. Strip cause from change, and only the bookkeeping survives, a set of operands and a statement of what each becomes. That table is a transformation, Ashby's atom, defined by what it does, never why. Everything downstream is built by iterating it. A transformation whose transforms are themselves operands is closed, and only a closed one can be reapplied indefinitely. The unclosed one takes one step and then jams. Iterate a closed, single-value transformation, and you have the abstract machine, its behavior, the trajectory of a representative point drifting toward a cycle or a rest state. The kinematic graph makes this visible. The algebra becomes a topology of basins. This vocabulary is the whole book's foundation. This section explains how cybernetics reframes what a theory of machines even asks. Cybernetics inverts the question. The older question was, what is this thing? Cybernetics asks instead, what does it do? Behavior is the object of study, not substance. Fix a variable's mode of behaving, say simple harmonic oscillation, and the carrier becomes irrelevant. It can be a point on a wheel or a potential in a circuit. The truths survive any change of matter, and they lean on no law of physics. Ashby's anchor is geometry. As abstract geometry outgrew terrestrial space and swallowed real objects as special cases, cybernetics stands the same way to the real machine, whether that machine is neural, mechanical, or economic. There is a second generative move. Treat a given machine by all the behaviors it could produce, never by the single act it performs here and now. Substrate independence, together with the space of the possible. That is what is new. This section explains Ashby's definition of the determinate machine. A machine is what it does. What it is made of does not enter the definition at all. Ashby's move is to define a determinate machine as anything whose behavior is a closed, single-valued transformation on its states. The state becomes the operand. The next state is its transform. A trajectory is the successive powers of that transformation. Single valuedness is just the demand that one state cannot lead to two. Substance drops out entirely. A clock, a bacterial culture, stickleback courtship, a cooling casting, all embody the same transformation if their state transitions match. So cybernetics studies the symbolic object and inherits every real system at once. This is definition by behavior rather than by construction. The whole job of the chapter, in part 1, is to install this correspondence, letting the algebra of transformations carry directly into physical dynamics. This section explains what a determinate machine is in the sense Ashby gives it. A determinate machine is whatever behaves like a closed, single-valued transformation. Ashby fixes the machine by what it does, never by the matter it is made of. Each state settles its successor uniquely. That uniqueness is determinateness itself, read straight off the constraint that every transform is single-valued. Letting 2, 3, or n time steps elapse just applies successive powers of the one transformation. The primitive to keep is this: identify a system with the transformation it enacts, and the substrate drops away. Beads on springs, a clock whose rule is n prime equals n plus k, Tinbergen's stickleback courtship, a perfectly well-defined transformation that is not even numerical. These are one pattern seen from 3 angles. Pen. On-paper transformation theory now binds to any real system theory, now binds to any real system that repeats its trajectory. This section explains Ashby's machine with input and why a parameter is what selects the machine. The core move is that a parameter selects the machine. When you set a parameter, you index which closed, single-valued transformation drives the states. The input is a pointer ranging over transformations. Its role is to select which transformation runs, sitting above the level of any single one's operands. 2 disjoint senses of change follow from this. The first is state to state, the machine's behavior under its own internal drive. The second is transformation to transformation, the switch thrown from outside that changes its way of behaving. The transducer simply is this indexed family, R sub A, and the parameter A is its input. Everything downstream, environment, control, regulation, becomes one system reaching into another's parameter slot. The knob lives above the states as their selector. This section explains how a machine acquires an input, following Ashby's 4th chapter. A machine acquires an input the moment you stop treating it as one transformation and treat it as a family, one transformation per setting of a knob. Ashby's move is to index the transformations by a symbol, the parameter, and that symbol is the input. Nothing is added to the machine. The parameter merely selects which of its latent behaviors runs. From this follow 2 categorically distinct changes that must never blur. The first is state to state, the machine's own behavior under internal drive. The second is transformation to transformation, imposed from outside by the experimenter. A crane and its driver, a nerve and its muscle, same structure, an operand steered by a parameter. Predict every control from this. Control is always a parameter reaching into a family. This section explains why Ashby refuses to let one word carry the idea of stability. A cube tips back onto its face, a cone does not, and Ashby will not let a single word name that difference. Stability decomposes. First, there is a fixed point, a state the transformation leaves unmoved, so that T of A equals A. Then there is attraction. Displace that state by a disturbance, D, and ask only whether the state comes back, whether the limit as ask only whether the state comes back, whether the limit as n grows without bound of T of A equals A again. What that test demands is return, the eventual coming back. It does not demand rest at every step along the way. The state may wander before it settles, and it still counts. Because the disturbance has to be named, the predicate is never a property of the system alone. It is defined relative to a specified set of disturbances. This is why a pencil that is stable against a 1-degree nudge is unstable against a 5-degree nudge. Change the named disturbance, and the verdict changes with it. The whole thesis of the chapter is this dissolution. The overburdened word stability is compound shorthand for 3 things: the states, the trajectories, and a specified return. Whenever the shorthand strains, substitute those 3 facts back in. This section explains why stability is best understood as closure, a property of states and their transformation rather than something a system possesses. Stability is not a property a system has. It is closure. A set of states is stable exactly when the transformation read at coarser grain, and no new state escapes. Equilibrium, the case where T of x equals x, is merely the one-point version. The cycle, the basin, the stable region are the same relation read at coarser grain. You test it operationally. Displace by D, apply T repeatedly, and watch whether T applied n times to D of returns to A. So the word dissolves into states and transformation, and because every aspect can be specified exactly, it is always dispensable shorthand. This is why positive feedback cannot adjudicate stability. Only the trajectory can. Predict every stability type from one question. What does T do to this set? This section explains the black box, the move that reduces any system to its behavior at the terminals. An object is defined entirely by what it does to what you feed it. Its material makeup plays no part. This is Ashby's move. Seal the mechanism, keep only the terminals, and couple experimenter to box into a feedback pair. Every fact you can win is then a recoding of the protocol, the logged sequence of input and output states. All that and nothing more. So a system's identity collapses to its transition, behavior taken up to isomorphism. Contents become invisible and, more sharply, irrelevant. This is the chapter's payload for the book's arc. It licenses treating brains, rats, economies, any real object at all as a black box, because substance never entered the epistemology in the first place. Only the flow of information across a boundary did. This section explains how the 6th chapter treats a sealed system, and what follows once you accept that its behavior is its whole identity. A sealed system is knowable only through what it does to inputs. Prizing open the casing yields nothing the input-output record did not already contain. Ashby's move is to make the casing constitutive rather than an obstacle. He couples the experimenter to the box as a feedback pair, logs the sequence of input state and output state, and then every deducible fact is a recoding of that log, all that state, and then every deducible fact is a recoding of that log. All that and nothing more, as Chapter 6 puts it. The system's identity collapses onto its behavior. The contents become surplus. This is the primitive that an object is what it does, the same universal property stance under which a determinate machine is later reconstructed canonically from behavior alone. The chapter converts cybernetics from a science of mechanisms into a science of protocols. This part introduces the seventh primitive, variety, the quantity that opens all of Ashby's Part 2. Regulation cannot be spoken of about a single thing doing a single thing. The questions only become answerable once you look at the set of what a thing might do. That is Ashby's move for the whole of Part 2. Stop studying the object, study its set of possibilities, and give that set a number. Variety is that number. It is the count of distinguishable elements, or the base 2 logarithm of that count, measured in bits. One primitive, and it carries the surprise that undoes the whole naive picture. Variety is not intrinsic to the set. Take the 2-arm semaphore. It offers 64 arm configurations, but only 36 of them to an observer who cannot tell the left arm from the right. Discriminatory power sets the count. The measure lives in the coupling of set and observer together, never in the set alone. This section explains Chapter 7, where the argument swaps one question for another. Stop asking what a thing is. Ask instead how many things it could have been. That swap, from the individual to the set of possibilities it was drawn from, is the whole chapter, and the hinge on which Part 2 pivots toward information. The measure is variety, the count of distinguishable states, or its logarithm in base 2, giving bits. A message informs only relative to its set. The two prisoners who both say "I am well" carry different amounts because their permitted alternatives differ, and variety even depends on the observer's power to discriminate. When one condition admits less variety than another, that shortfall is constraint. The single primitive everything downstream regulates with. This part explains what a code preserves when a message passes through a machine. A coding is nothing but a transformation, and its operand is the whole message, not the letter. So the question, what survives passage through a machine, becomes the question, what does a transformation conserve? The invariant is variety. A 1-1 transformation leaves the size of the set of possibilities untouched, and only a 1-1 transformation leaves the size of the set of possibilities untouched, and only a 1-1 map has a single Bolyud inversion. That single fact governs everything downstream. A message is recoverable through a chain of codes, exactly when every stage preserves variety. Because the moment two messages collapse to one form, the receiver cannot tell which was sent. The machine itself is just such a coder. Its transducer table is its transducer table, is its transformation. Conservation under an invertible map is the primitive. Recognize it, and decodability, information, and channel capacity all follow. This section explains how a message behaves inside a determinate machine, and it turns on a single primitive. A message moving through a determinate machine is recoded rather than carried, and the whole chapter falls out of one idea. Coding is a transformation on the set of possible messages, never on any single one. A 1-to-1 transformation preserves variety, so distinctions lost nowhere can always be recovered. An inverter is buildable, whatever the material, neuronic or hydraulic. Only determinateness and the conservation of distinction matter. Here is the correction that makes the whole picture cohere. Variety never lives inside a transducer. A single machine at a moment is in one state. Variety exists only across a set of replicates. This is the bridge from the variety of Chapter 7 to regulation. It is the ledger. A regulator must later balance. This section explains why an incessant transmission needs a new kind of machine. Start with the constraint. A determinate machine of finite size must eventually cycle. Its trajectory cannot run forever, so it cannot model a nerve or a cable that carries messages without end. That is the wall a single-value transformation runs into. Ashby's move is to loosen the single-valued transformation into one where each state carries a constant probability of passing to each other's state. This is the stochastic transformation, and its sustained sequence is the Markov chain. The whole load of the chapter sits in one inversion, Chapter 9 against Chapter 3. Determinism is the extreme corner of chance, the stochastic matrix in which every probability has collapsed to 0 or 1. Everything prior in the book becomes one slice of this wider object. That unity is what carries indefinite transmission, and it seeds Part 3's account of regulation. This section explains how Ashby loosens the determinate machine into the Markov chain. Begin with the problem. An endless message defeats the determinate machine. No finite single-valued system has an infinitely long trajectory, so it must eventually cycle. Ashby's move is to loosen the transformation. Let each state carry a whole spread of probability over its successors rather than a single fixed one, a constant transition matrix, the Markov chain. The determinate machine survives inside this. It is absorbed as the extreme case where every probability is 0 or 1. That is the whole primitive. Determinism is stochasticity with the weights pinned. Constant probability earns its meaning operationally. It is a constant frequency, checkable by experiment, never felt as confidence. From this one generalization, the regulators of Part 3 all follow. The insect drifting between water, pebble, and bank is its first live specimen. This section explains regulation in biological systems, and it compresses the whole chapter into a single move. Survival is the stability of a set. That is the move. A mouse's states split into two kinds, the living states and the rest. The living states are a chosen subset, call it eta. The cat is in operation, and survival is the operation keeping you inside eta. Natural selection, then, reads as a search for a regulator. Call the regulator F. It sits between a disturbance, call it D, and the essential variables, call them E. The dependency runs D leads to F, and F leads to E. The measure of F is startling. A good regulator blocks the flow of variety from D to E. It is so good that E carries no information about D. Ashby's water bath, call it B, wins precisely because its record tells you nothing of the weather. Regulation, survival, and information collapse into one quantity. The next chapter bounds that quantity exactly. This section explains why survival, regulation, and information are one idea. Survival is just the stability of a set. The mouse that leaves the affair with the cat still inside its physiological subset has survived, nothing more mystical than a trajectory staying within bounds. Ashby's chapter earns its place in Part 3 by fusing three words, regulation, information, and survival, into one diagram. D leads to F, leads to E, disturbance through the regulator to the essential variables. The regulator's whole job, stated as its defining behavior, is to block the flow of variety from D to E. The good thermostat, autopilot, or fencer leaves you unable to infer the disturbance from the essential variable. A perfect regulator is one you cannot see working. Natural selection favors whatever interposes such an F. Everything downstream is this claim, made quantitative. This section explains Ashby's law of requisite variety, the ceiling on what any regulator can achieve. A regulator cancels disturbance only by matching it. Move for move for move, whatever variety the world throws, the controller must own at least as much to hold the outcome fixed. Ashby strips regulation down to a game. D perturbs, R responds, and in any table where no column repeats, the residual variety of outcomes cannot fall below the variety of D minus the variety of R. The minimum achievable disorder is set by a subtraction, not by cleverness. Only variety can destroy variety. This is the conservation law running under every thermostat, immune system, and government. Control is bounded by channel capacity. The chapter is the book's pivot from describing machines to measuring the hard ceiling on what any regulation can achieve. This section explains Ashby's law of requisite variety, the single bound that governs all regulation. Regulation is capped by one inequality. A regulator can cancel only as much disturbance as it can itself match. Move for move. Ashby strips the idea to a game. D plays a disturbance, R answers, and a fixed table fixes the outcome. R succeeds when it steers every outcome into the acceptable set. The result is arithmetic. The residual variety of outcomes cannot fall below D's variety divided by R's. Written logarithmically, the outcome variety VO is greater than or equal to the disturbance variety VD minus the regulator variety VR. Only variety can destroy variety. This primitive seeds the whole book. Regulation is a communication channel, its power capped by channel capacity. What the law forbids is the free lunch. No cleverness buys constancy that R's own repertoire cannot pay for. This section explains the error-controlled regulator, the loop that corrects by responding to damage rather than by foreknowledge. Deny the regulator. Advance warning and one channel survives, the damage itself. The thermostat learns of the cold flask only once the water already cools. Information about the disturbance. D reaches R by the longer route from D to T to E to R through the very variable R exists to protect. This is the closed loop. Feedback from outcome, back to regulator. The primitive is this. Regulation by cause needs foreknowledge. Regulation by error trades that foreknowledge for a signal that must first go wrong. Hence the price the chapter extracts. In section 12.5, an error-controlled regulator cannot be perfect. To be informed at all, it must admit the error it corrects. This section explains how a regulator that cannot see the disturbance still corrects for it. A regulator that cannot see the disturbance reads it off its own damage. Ashby reroutes the regulator's information about the cause through the long path from the disturbance, D, to the target T, to the error E, and finally to the regulator R. The regulator acts on the error it has already suffered, not on the threat that produced it. The generative move, when the cause is invisible, let it write itself into the outcome and correct from that trace. Its price is exact. Such a regulator cannot be perfect because holding the error constant blocks the very channel feeding the regulator. Success starves its own sensor. Error must be permitted to inform the correction of error. This section explains why regulating a very large system is not a new problem, only the same regulation problem seen at scale. Largeness is a decoy. The chapter's whole move is to refuse size as an explanatory variable. Every proposition of the theory so far was stated so that the number of parts drops out, so the very large system is the same regulation problem you already understand, and what actually makes it hard is the variety in the disturbances, which only correlates with size. Under a regulator whose channel capacity is fixed, requisite variety sets an absolute ceiling that no internal cleverness can lift. The single lever left is discovering constraint in the disturbances. Constraint alone converts regulation impossible into regulation possible. Ashby's parallel to Fisher and Shannon lands the point. Approach the very large system with no extravagant ideas of what is achievable. This section explains why a very large system resists regulation and where the only exit lies. Size is a decoy. What makes the very large system resist regulation is the variety its disturbances carry, not the sheer count of its parts. Requisite variety fixes an absolute, size-invariant ceiling on what a bounded regulator can absorb, a ceiling that stays uncrossable however cleverly the parts are rearranged. The chapter makes a single move. Name the real obstacle, then find its only exit. Every constraint hiding in the disturbances, their repetition, their loose coupling, their reducibility, drops the true variety below the first estimate. That conversion is what turns regulation impossible into regulation possible. That is the biologist's entire leverage once her channel capacity is fixed, and it cedes the book's closing turn. To design a regulator is to select one machine from many, and selection is itself an act of regulation, so a regulator can only be built by another regulator. This section explains why amplifying regulation is possible at all. An amplifier never magnifies. It gates. Give it a little, and it releases a lot, but the lot was already sitting in a reservoir, the input merely steering the flow. The crane driver lifts tons because coal, not his arm, does the lifting. The law of requisite variety forbids conjuring regulation from nothing, exactly as conservation of energy forbids conjuring power. Yet neither forbids supplementation. The escape is staging. Split the act in two. Let a small selection build a regulator. R1, that in turn builds the large regulator. R2, the surplus variety drawn from an abundant source. That is why the gene pattern never specifies the brain directly. It builds R1, and the environment supplies the rest. This section explains why an amplifier never magnifies. It gates a reservoir. Give it a little sound, power, money, and a lot comes out. But the surplus was always sitting in the reservoir, and the input merely selects the flow. Ashby's move, the law of requisite variety, forbids amplifying regulation directly, exactly as conservation of energy forbids amplifying power. Both permit supplementation. Neither permits magnification. The trick is staging. A small selection at stage 1 provisions a far larger regulator at stage 2, which draws its variety from an abundant source elsewhere. The boy lifts the heavy weight because his father is willing to. Requisite. Variety is the conservation law. Two-stage supplementation is how you appear to beat it without breaking it.